Hello everyone, welcome to Parthiva Tech. In this video, we will solve the problem of the day question on GeeksForGeeks for 18th April 2023. The problem statement for today is minimum BST Sum Subtree. This problem is based on binary search tree concept. Let's now open this problem to solve it. Let's go through and understand the given problem statement. The given problem statement says, given a binary tree and a target, find the length of minimum subtree with the sum equal to the target, which is also a binary search tree. Okay, so here we will be provided with a binary tree. We have to check that if it is a binary search tree, then we have to calculate the sum of all the nodes value and we have to match it with the target, which is again given in the input. And if both these conditions satisfy, that is it is a valid binary search tree and the sum is matching, then we have to return the length of the minimum subtree where we got these two output. Okay, so let's go through the given examples here. So the first example says this is the given binary tree. So here and here the target is 38. So here the output is 3. In explanation, it is given as 5, 17, 16 is the smallest subtree with length 3. Okay, so here if we can see in this one, if we calculate the summation of this 5, 17 and 16, then this subtree 5, 17 and 16, this subtree gives the summation of all these nodes, gives the value as the target which is there in the input. So that's why and how many nodes are involved? 3 nodes are involved. So that's why that output is 3. That's why it is written as 5, 17 and 16 the smallest subtree with length 3. Okay, if you go to the second example, then the second example says this is the given binary tree. Here the target is 73. Here the output is -1. No subtree in the BST is BST for the given target. Okay, so if you try to look at this one, then we are not getting this desired output of a target element from this given tree. That's why this is here the output is -1. Okay, so I hope the problem statement is clear. So we have to simply check that each subtree is a valid BST, and if it is, then we have to calculate the sum of all the nodes and we have to check whether the summation is equal to the target or not. If it is, then okay, then we return the length of that subtree, and if it is not, then we move to the next subtree and we check the same thing. Okay, so the approach to solve this problem is to traverse the entire tree and for each node check if it is the and we'll check if the subtree rooted at that node is valid BST. If it is, then calculate the sum of the subtree rooted at that node, and if the sum is equal to the target, then update the minimum subtree size found so far. Okay, so this approach we will be following. So how it will work? So it will first start with since we will be traversing the entire tree for each node. So we will start from 13. Then we will check if it is a valid BST or not. Yes, here we can see it is valid BST. What is the property of BST? That means to the left of it, all the elements should be smaller, and to the right of it, all the elements should be bigger. So this is the property of binary search tree. So that means when we do in order traversal of that binary tree, then it should give all the elements in ascending order. Okay, so so here we can check, yes, for 13 it is a valid BST, and if it is valid BST, then we try to get the sum. So it will add 13, 5, 17 and 16. Then here we can see the summation is greater than 38. Okay, so that's why this binary tree is discarded. Then what we will do, we will move to the left subtree. Here the left subtree starts with 5. So to the left of subtree, here it is null. So so this cannot be taken into consideration. So for the remaining part of this subtree, it is 5, 17 and 16. So here we can see we have got the output as if we add all of these, then we get the output as 38. so it will return the length as 3 only from this one. Okay, so in this case it is not required to go to the even right subtree of 13. Okay, so here since it in left subtree it was null, so this was not taken, so only the right subtree including the node for this subtree which is involving 5, 17 and 16, that is giving the desired target, that is of 38 when we add all these 3 nodes. So that's why the output is 13. I hope the approach is clear what all things we will be doing in this problem. Okay, so with this approach only I have prepared the solution. Let me just copy it here. I'll explain it line by line that what all steps we are doing here. But again, majorly we are doing those 3 kind of operation. We are traversing the entire tree. Then for each node, we check if the subtree rooted at that node is valid BST. If it is, then we get the sum of the subtree rooted at that node. And if the sum is equal to the target, then we update the minimum subtree found so far. Okay. So so these 3 steps we will be following in this code as well. So let me just copy it here. So here again I have added comments against each line so that it becomes self-explanatory. So first of all, we have initialized minimum subtree sum to the maximum value of the integer. Okay, then the function minimum minimum subtree sum BST, it takes 2 arguments, that is target and root, which represents the target value and the root of the binary search tree respectively. Initially it initializes the minimum subtree variable to a maximum, this one whatever we have done here, that it initializes the minimum subtree sum variable to the maximum integer value, and then call the solve method, this one. Then we call the solve method, solve function to find the minimum subtree size whose sum is equal to target. If no subtree is found, then it returns -1. Okay, so we are calling the solve method to find the minimum subtree sum. But if the subtree sum is not updated during traversal, then we return -1. Okay, so for that reason it said that if no subtree is found, then return -1, else it returns the minimum subtree size found. Okay, so when we talk about this, so this was the initial method. So here from here the flow goes to solve method. So when we talk about the solve method, then the solve method again takes 2 arguments, that is root and target. It is a recursive function that traverses the binary search tree in the depth first manner. For each node, it first checks if it is a leaf node, and if its value is equal to the target value. If it is, then it updates the minimum subtree sum variable to 1, since the subtree containing only that node that has the sum equal to the target value and has size 1, and from here only it returns. But if the node is not a leaf node or its value is not equal to target value, then it checks if the subtree rooted at that node is valid BST using the check BST function. Okay, so if this condition is not true, then we are checking if the subtree rooted at a particular node is valid BST. For that we are calling this method. Okay, using this check BST method. If it is, then it calculates the sum of the subtree rooted at that node using getSum function, which also counts the number of nodes in that tree. If the sum is equal to the target value, it updates the minimum subtree sum variable to the minimum of the count of the current value and the size of the subtree found, which is the count variable in the getSum function. Okay, and finally here the solve function recursively calls itself for the left and the right children of the current node to explore the entire binary search tree. Okay, then from here so this was the complete flow, but internally we again using two function, which is check BST and getSum. So we'll see what all things are there in check BST and getSum function. So check BST function takes 3 arguments, that is root, minimum value and maximum value, and checks if the subtree rooted at subtree rooted at root node is a valid binary tree binary search tree with values between minimum and maximum value. Okay, again, so here in this function we check if the subtree rooted at root node is a valid binary search tree with values between min val and max val. It returns true if the subtree is valid BST and false otherwise. Okay, so here we are checking that everything that whatever the value is there, so it is currently and that it is following all the properties of BST or not. Okay, so that's why we are checking. It should be the root data should be lower than the minimum value, and if it is outside the range, then it is not a BST. Then we return from here. Else we check the left and the right subtree, that are they also BST or not. Okay, so this was the check BST helper function to check if the given tree is a binary search tree or not. The next method we have get sum method. It again takes two arguments, which is root and count, and calculate the sum of the subtree rooted at root node while also counting the number of nodes in the subtree. It returns the sum of the subtree. So this get sum function calculates the sum of the subtree starting at any particular root node, and it calculates the sum of the entire subtree, and it returns the sum. And it also counts that how many nodes are involved in this summation operation. Okay, so here again, so this was the complete coding part of it. So here if you can see, so in this one, this was the given input method here. So from this we call solve method, which is the main driver function of this solution. So in solve method, we check the sum edge cases. If root is equal to null, then return. Then we again check if the root node is a leaf node and it matches the target, then we update minimum subtree sum is equal to 1 and we return from there. If it is not the case, then it goes into the recursive call operations to try calculating the sum of all the BSTs which we encounter and try to find a summation for each subtree. Before that, it first check that any subtree rooted at a particular node checks whether that is a valid BST or not. If it is valid BST, then only we will get the sum of all the nodes there, and we check if the sum is equal to target, then we update that how many nodes were involved in that, or what is the size of the length of the minimum subtree which is giving this sum which is equal to the target. If that is done, then we simply, this is getting updated, and once this is getting updated, since we have defined it as a global variable, so we can directly return this one, return the minimum subtree sum. Okay, so we are directly returning that variable here. We do not have to return anything from this solve method. It is defined as a global variable. So for that we are using check BST as a helper method and get sum as a helper method. Check BST checks if it is a valid binary search tree, and get sum is used to get the sum of all the nodes that is involved in that subtree, binary search tree subtree. Okay, so I hope the entire solution is clear to you, the what all steps are involved and how we are approaching to the solution and how we are solving it. So let's try compiling this code. So here we can see we have got correct output for the given input here. Let's try submitting the solution. So here we can see we have got all the test cases covered for this Java solution. So this problem helped me solve successfully in Java. So talking about the time complexity of this method, it is in the order of big O of n square. That means when I'm talking about this method, so mainly we are calling this solve method. So I'm talking about the solve method, solve function. So it is in the order of big O of n square, where n is the number of nodes in the binary tree. The solve function calls the BST function, which itself has a time complexity of big O of n, since it visits each node of the tree once. Then for each node it satisfies that BST property. Okay, and then for each node that satisfies the BST property, the solve function calls the get sum function. That means here, if this condition is valid, if we are getting true for check BST, then we are calling the getSum function, which also has a time complexity of big of n, because each visits each node of the subtree once to compute the sum. Therefore, the worst case time complexity of the solve function is big of n square, which occurs when every node of the tree satisfies the BST property and has to be processed by getSum function. But if it is not the case, that if every node is not a valid BST, then that part would be skipped and we will get a time complexity which will be lesser than big of n square. Okay, so since that minimum subtree sum BST function calls the solve method once, the overall time complexity is again the same whatever is that for that solve function, which is in the order of big of n square in worst case. Okay, so this was the Java solution of it. I have even prepared C++ solution. Let's move to the C++ editor. I'll again just copy it here. Something went wrong. Okay, let me just copy it, try copying it again. Something didn't work. Yeah, so this time it is fine. So again, here also the logic is completely same, only the syntactical difference whatever we have between C++ and Java, that only is there, because here in Java we had created it was mentioning to, if you move to this, then this node was there. What was the node? Node was a class. But in C++, here we have the concept of pointers here. So we are using pointers here. So that the difference which we get between C++ and Java, that is the here. Apart from that, entire logic is same only. Here also we from this minimum subtree sum BST, we enter into solve method. We check the some boundary conditions. After that, we check for the BST, and if it is that, then we call the getSum function and we try to execute the complete thing. So this was the check BST function. So solve method is here. We are checking the boundary condition. We first check the if it is valid BST, then we call the getSum function and we update the minimum subtree sum variable. And again, getSum is used to get the sum of the particular subtree, and check BST checks whether the particular subtree is a valid BST or not. So the complete logic is entirely same. Let's try compiling this C++ solution. So for this, even for this, we have got correct output. Let's try submitting this solution. So even our C++ solution is giving all the test cases covered. It is giving the correct output. It has covered all the test cases. Yeah, so this problem has been solved successfully using both C++ and Java language. Yeah, so that's all in this video. I'll provide the link for this question in the description box, and even the link for the solution code in these two languages. Even that I'll provide in the description box. Please do check that. So please like, comment, and share the video, and please subscribe to the channel for more upcoming videos. Thank you for watching.